the simplest example of a molecule that is polar is probably HCl. HCl is polar because the electronegativity of the chlorine atom is greater than the electronegativity of the hydrogen atom. And so as a result, the chlorine will pull the electron density away from hydrogen toward chlorine. And so we symbolize that with an arrow with a plus sign on the end, and the arrow points in the direction of the more electronegative atom, and it leaves the plus sign in the direction of the less electronegative atom. And so this is symbolic of a pull of electrons from the hydrogen toward the chlorine. All right, let's look at the bromine molecule, Br2. In this molecule, there is no difference in electronegativity between the two bonded atoms. So in this molecule, there is no dipole. There's no way to draw an arrow with a plus sign on one end and an arrow on the other pointing towards the electronegative atom, because these atoms have the same value for the electronegativity. So this molecule is nonpolar. In an earlier video, I mentioned that in order to assess a molecule's status as polar or nonpolar, we would have to know the shape of the molecule. And then I said in order to know the shape of the molecule, we had to know its Lewis structure. So we've done all this work. How do we determine whether or not a molecule is polar or not? By looking at the shape. So let's look at some examples. First example we're going to look at is carbon dioxide, CO2. CO2 is going to have a shape that is linear, and so we'll draw that shape here. And you can see that the oxygens are directly across from each other. Now, the oxygens are going to create a pull of electrons from the carbon because they are more electronegative, and so this is going to create a dipole in both directions. Now, this dipole, since the pulls are equal in magnitude and opposite in direction, that is, they are pulling directly opposite each other on the carbon since it's a linear molecule, these pulls are actually going to cancel each other out. And so this molecule is nonpolar. Let's contrast carbon dioxide with a molecule like HCN. HCN is a polar molecule. The reason it's polar is because it has an unequal pull on the central atom. So if we look at the nitrogen is more electronegative than the carbon, so there will be a pull of electrons from the carbon toward the nitrogen, which is going to leave the carbon a little bit positive. Now, carbon is a little bit more electronegative than hydrogen, so there will also be a pull in the direction of carbon on the hydrogen. So HCN is a polar molecule because these pulls, these dipoles, they do not cancel each other out. And so whenever the dipoles do not cancel each other out, we have a situation where the molecule is polar. One of the most famous polar molecules is water. And if we look at water, we can see why it's polar. Since we know that water is a tetrahedral molecule, and it is not as what we would sometimes want to draw straight across from each other like this. All right, this is not what water looks like, and we know that now. We know that water has a three-dimensional structure. It is bent, and we know that the oxygen is pulling the electrons from the hydrogen. So the oxygen creates a dipole because the oxygen is more electronegative than the hydrogen, So it creates a dipole where it leaves the hydrogen atoms on the positive side and the oxygen is a little bit negative. However, since the poles are not directly across from each other, they do not cancel each other out. And so since they don't cancel each other out, this one is a polar molecule. Let's look at methane, CH4. Methane is a nonpolar molecule. And the reason it's nonpolar is because the carbon is going to be electronegative and it's going to pull electrons from the hydrogens. And so it creates a dipole in each direction. But since the dipoles all converge on a central point and the dipoles are all of the same magnitude, they all cancel each other out, and this molecule is nonpolar. This molecule is the nitrate ion, NO3-. I've drawn the 3 resonance structures for the nitrate ion. And when you look at just one of those resonance structures, you would see that perhaps one of the nitrogens is double bonded and the other 2 are singly bonded. And so this structure would be polar. But when you remember that resonance structures are actually a mixture where the actual structure of the nitrate ion is a mixture of all 3 resonance structures, then it becomes more obvious that this is a nonpolar molecule. And the reason is because each one of these bonds can be thought of as having a bit of a partial bond and a full bond. And so the NO3- anion will be nonpolar. Let's consider the molecule CH3Cl, chloromethane. Is this molecule polar or nonpolar? We need to consider the electronegativities of the bonded atoms. In this case, chlorine is more electronegative than carbon, and so chlorine will create a dipole where it pulls electrons toward it and leaves the carbon as positive. The carbon is more electronegative than the hydrogen, so it's going to create a dipole between the carbon and the hydrogen where it pulls electrons toward the carbon. And so that's going to be the case in all 3 of the hydrogens that are bonded. Now, we can see that these dipoles do not converge into a single point, that is the central atom, and they are not all the same because chlorine and hydrogen do not have the same electronegativity values. And so these dipole moments do not cancel out. In other words, the red arrows with the plus signs on them do not add up to 0. And so this molecule is polar. Let's consider carbon tetrachloride. In this molecule, we have chlorine that's going to be more electronegative than the carbon. So chlorine will pull the electrons away from the carbon. And since there are 4 chlorines and they are all bonded together to the carbon atom, and the geometry is tetrahedral, so the pulls created by these chlorine atoms will all cancel each other out. And as a result of this cancellation, carbon tetrachloride is nonpolar.